In lecture 7, we will discuss the magnitude comparator or digital comparator, and 1-bit comparator, 2-bit comparator, and this is general case we will discuss a 4-bit, how we can extend the concept to higher bits. And we will also introduce one IC which is 7485, which can be used for to compare 4-bit or higher values. Okay. And in digital domain, a magnitude comparator will be like this. Will work with the help of a 3 binary variable. Okay, and if there is 2 values a and b, okay, we need to compare this a and b. So there are 3 different cases. It can be a equal to b, so which is indicated as e. If a equal to b, we will say that the variable e will be equal to 1. Okay, and if a is greater than b, we will say the output line g will be equal to 1. And if a is less than b, we will say that the line L is equal to 1. So 3 output line will be there, E, G, L. And with respect to the input values, input binary bits, we need to calculate whether E is equal to 1 or G is equal to 1 or L is equal to 1. So it will compare the magnitude of the values. And we can discuss with 1-bit magnitude comparator. So for 1-bit magnitude comparator, there will be 2 inputs. This is the first input, we will call it as A, and the second input is B. Only 1 bit, so we will indicate A0 and B0. And the output will contain 3 different lines, E, G, L. So we already mentioned that if A equal to B, it is indicated as E. If A is greater than B, so always choose A as the first number. Then or A0 is greater than B0, or in binary terms A0 is equal to B0. Here A0 is less than B0. Okay. So A and B, you can consider as the input values and 3 output lines. This is the one output line, this is another output, and this is another output line. For example, 2 inputs, you will get 4 different combinations. If A equal to 0, B equal to 0, means A equal to B. So only E will be equal to 1 and all other output line will be 0. If you compare this next combination 0 and 1, here A is equal to 0, B equal to 1, means A is not equal to B, so this line will be 0. Only in this case A is less than B, because A 0, B 1, so only L equal to 1, that is A less than B condition will be true and all other condition will be false. So false will be indicated as 0. And in the third combination, A is equal to 1, B is equal to 0, so A greater than B actually. So the G line will be equal to 1 and all other lines will be 0. Now the last case, A equal to B, again 1, 1. So equal line will be 1 and all other output line will be equal to 0. So now we can design each output line with respect to the input combination A0 and B0. So we need to design L, E, G. Okay. So first we can design for L, that is A0 is less than B0, L is equal to 1. So L line is equal to 1 only in this particular combination. So this is a one combination where A equal to 0, B equal to 1. So you can write A0 bar B0. Okay, this is a design equation for L. Now we can design A equal to B condition. So this is the first case, design for L, and this is for E. That is A0 is equal to B0. A0 is equal to B0 means this is line E, and in the case of E equal to 1 in both 2 cases, when A0 is equal to B0 and A0 is equal to 0, 0 and 1, 1. So 2 combinations. So you can write here it is A0 bar B0 bar, and here it is A0 B0. So you can write like this, so which is equal to A0 B0 XNOR operation, or in other words we can say A0 B0. Okay, and we already studied when we discussed the XNOR gate. XNOR gate can be used as the equality checker. Okay, So whenever we want to check two binary values are same, we can use the XNOR gate. So XNOR gate is known as the equality checker, and XOR gate is known as the inequality checker. But in this case, we need to check equality, so we can use XNOR gate. So this is a direct case. So when you design this particular circuit, you will get a XNOR gate. And last case is a design for G, and for G, you can see that there is only one possibility. Okay. Only one case where you will get G is equal to 1, that is A0 B0 bar. So this is a G design, A0 and B0 bar. Okay, and now we need to draw the circuit diagram. So this is a circuit diagram which implement these functions E, G and L. So here you can say simplified diagram. This is A bar, actually generally written as AI and BI. Okay, for example, you can write A0 and B0. If A0 is here, you can write A bar, and here it is B, or you can write A0 B0. So you'll get A0 bar B0. Okay, so you got L function. Now the lower case is a G line. So here you'll get this is A0 and this is B0 bar. So you can write A0 and B0 bar. Now we got a G. Now we need E, and this is a NOR gate. So already we got A0 bar B0 plus is a NOR gate, so you can write A0 B0 bar the whole bar, so which is equal to lower portion is actually XOR expression and the whole bar, which is equal to NOR operation. Okay, either you can use this particular circuit, or you can directly connect an XNOR gate to implement A and B to implement E function. Either you can use an XNOR gate, or you can use this particular logic to implement E, L and G. Okay. Now we'll discuss a 2-bit comparator. If you take the example of a 2-bit comparator, again one thing is important. Again, two values A and B, but A contain two binary values, A1 and A0. A0 LSB, A1 will be the MSB bit. And B, if we compare B1 and B0, B1 will be the MSB of the second. So this is the LSB, and here also the LSB. So total 4 input lines and 3 output lines. Okay. When you take a 2-bit comparator, A1 A0 will be one value and B1 B0 will be another value. So we'll get different combinations, and now we need to check each bit. Okay, then only we can say what are the different values, whether A is greater than B, or A is less than B, or A equal to B. Okay. Now we can discuss about the truth table. So you'll get 4 combinations. For example, A means it's A1 A0. So you need to write 0 0, and for B, B1 B0. So if you take 2 bits, you will get 4 combinations, 1 0 1 1. So we need to check 0 0 with 0 0, 0 1, and 1 0 and 1 1. So for each value of A, you will get 4 combinations. So if you write like this, first you can say 0 0, you need to compare with 0 0. Okay, this is A actually, and this is B. Okay, these two values represent A. And after completing this, again we need to compare the other combination of A, that is 0 1. We need to compare with all other values. After that, we need to compare 1 0 and finally 1 1. So this is 0 1, and this is 1 0 and 1 1. Okay. Otherwise, we can write the 4 binary sequence directly. There's no problem. You can write the binary sequence. You can consider as a 4-bit. You can write from 0 to 15 the binary sequence. And you can take the first case. Here it is A1 A0 is 0 0, and B1 B0 is 0 0. In this particular case, it's equal. Okay, so you can see that A equal to B will be 1, and all other values will be 0. Now we can consider 0 0 with 0 1. Okay, here you can see 0 1 is greater. Okay, A is less. Okay, so you can see that this is actually G, and this is E, and this is L. So L line will be 1. Okay. Again, if you take 0 0 with 1 0, okay, 1 0 is greater, or we can say L line will be equal to 1 because A is less. Okay. Here also you can consider A 0 0 and B is equal to 1 1. So 0 and 3. If we compare 0 and 3, 0 less than b. So 0 less than 3 or L line will be equal to 1. Now similarly you can consider the other case 0 1 with 0 0. So 0 1 means 1 and b is equal to 0. If we compare 1 and 0, 1 is greater. So G line will be equal to 1. Next case you can see both values are equal, so A line will be 1. And similarly if you follow it's 1 and 2. This is 1 and this is 2. So A is less than B, so we can write L line will be equal to 1. Next case also 1 and 3. So 1 and 3, again A is less than. Now we can see that 2 with 0, so greater, and A is greater. Again 2 with 1, A greater. Here equal, A equal to B. Now A is less than B. So here L is equal to 1. In the last case, you can see 3, you can compare with 0. So it will be greater. Again 3 with 1, again greater, A greater. A and 3 and 2, if we compare, A is greater. And finally it is equal, so E line will be equal to 1. Now we need to design each case. So first we can design G. Okay. So now we can design, this is G line. Okay. If we take G line, here you can see that this is 1, this is 1, and based on this we can write 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So you can look at the corresponding values. There will be 4. Okay, 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. So if you take these values, you can say the 4 is equal to 1, 8 and 9. So okay, 8 and 9 is equal to 1. Then 12, 13, 14. So 12, 13, 14 equal to 1. So now we can group this. So if you group here, you will get A1, and here you will get in column wise you will get B1 bar. Okay. So A1 and B1 bar, and here you can if you take this particular group, it's A1 A0 and row wise, column wise you will get B0 bar. Okay. And if you consider this particular group, it becomes A0 bar, sorry, it's not A0 bar, it's simply A0, A0 and B1 bar and B0 bar. So I think we got all the terms. So G you can design like this. Similarly, you need to design for E. If we take E, again we need to identify the 1 values when will be equal to 1. So you can sequence values, you can put 0 to 15, and you can indicate the corresponding values in the truth table, and corresponding terms you can write. If you look at this, is again diagonal 1, and we know that diagonal and this in the opposite direction, so we can call it as an XNOR operation. Okay. So if you group this particular term, you will get after simplification you can see that A0 B0 and A0 bar B0, and into A1 B1 into A1 bar into B1. So okay, after you will get 4 different terms. The 4 different terms are written here. Okay, this is 1 actually, so 1 is written here. Next one is 2 actually. I think this is 2. This is 2, and this is the third term. So this is 3, and finally this is 4. So fourth term. And after grouping, you will get this is an XNOR operation actually. So you can write A0 XNOR B0, and here also A1 XNOR. So you can write A1, A0 XNOR B0 and A1 XNOR B1. Or we can see in another way, if 2 numbers are equal, 2 binary bits are equal. So A1 and A0 means each bit should be equal. That is 1 1. For example, A1 A0, 2 possibilities, B1 B0. Okay, this is one possibility. Then each bit A1 B1 should be equal to 1. So that's why we are checking here. and A0 B0 should be equal to. If both 1, the output is equal to. So we need to AND. Or another combination is this. Okay, in both case, both bits corresponding bits should be equal to 1. So this is simply an XNOR operation. Now the last case, that is A less than B. In the similar way we can approach, and finally you will get 3 terms. You can group all these terms. So corresponding values you can write in the Kmap, and you need to solve this Kmap. After simplification of the Kmap, you will get like this. And now we need to draw this comparator circuit, 2-bit comparator circuit. So we can indicate A1, A0, B1, B0, and its complement also A1 bar, A0 bar, B1 bar, B0 bar. Okay. Now first we need to A greater than B. For A greater than B, this is the function A greater than B. So corresponding terms you need to indicate. Here it is A0. Then second term is B1 bar. So this is B1 bar, and the third term is B0 bar. So here you can write A0, B1 bar, and B0 bar. Similarly, you can check the second one also, and finally all these values are connected to an OR gate. Okay. So this is a circuit diagram. A0 and A equal to B is simply an XNOR gate, and we need to take the AND operation. So here you can see the AND gate. Okay, this is an XNOR gate. So 2 XNOR gates. So this is an XNOR gate. This is also XNOR gate, and there is an AND operation. Finally, this is actually G function. This is E function, and this is L function. Now we can discuss a 4-bit comparator. The same concept you can extend, but it's not that much easy when you write the truth table of a 4-bit. For 4, you'll need to write 8 binary values, and the truth table will be very big, and it's very difficult to design. So we will use another concept approach here. So we can consider the first 4-bit number A is equal to A3, A2, A1, A0, and second number B is equal to B3, B2, B1, B0, where A3, in this case A3 is equal to MSB, here B3 is equal to MSB, A0 is considered as LSB, here B0 is considered as LSB, least significant bit. And 3 output line, A equal to B, A less than B is L, and A greater than B is G. Okay, and now we can check that 2 values. Okay, these 2 binary bits are we need to compare. Each binary digit is a 4-bit wide. So we can take the first case, if A3 is equal to 1 and B3 equal to 0. So for example, 1 0 1 0 and 0 1 1 1. If we compare these 2 values, this is A and this is B. So this is A3 and this is B3. Okay, if you want to compare 2 values, which one is greater? So from this particular example, we know that if A3 is equal to if A3 is equal to 1 and B3 is equal to 0, we can say that A value is higher. Okay, by checking the most significant bit, we can say that A3 is 1 and B3 is equal to 0. We know that A value is greater. So definitely you can conclude that if A3 is equal to 1 and B3 equal to 0, then A is greater than B. Okay, so we got one possibility. Next case is OR, if both values are same, or otherwise we can say it's low if both values are same. For example, it's 1 1 1 0 0 1, something like this. Okay, if first 2 values are equal, that is A3 and B3 are equal. So this is the case, A3 and B3 are equal. Then we will check this next 2 values, that A2 and B2 will check. If A2 equal to 1 and B2 equal to 0, definitely we can say that A is greater than B, because first value is same. So next significant bit is A2 and B2. If A2 is 1, definitely that A value will be high. Okay, so that is the case. And again, if the first 2 values are equal, that A3 and B3 equal and A2 B2 equal. So next case is something like this. Okay, and we need to compare. So A1 and B1. So A3 B3 equal, A2 B2 equal, then A1 B1. Then A1 is equal to 1 and B1 is equal to 0. Definitely you can say A is greater than B. Again, there is one more possibility, 1 1 1 and 1 1 1 0. So first 3 bits are equal. A3 equal to B3, A2 equal to B2, A1 is equal to B1. If it is like this, then you need to check the last bit or least significant bit, A0 and B0. If A0 is equal to 1, B0 is equal to 0, definitely you can say A greater than B. Otherwise, L value is equal to 1. So this is the design equation for G. Otherwise, we can say A less than B. Okay. Now, we need to check if values are equal. If two values are equal, A3 equal to B3, A2 equal to B2, A1 equal to B1, A0 is equal to B0. So definitely you can use an equality checker. Equality checker means an XNOR gate. So XNOR operation we can write. So this is the E function. That is a XNOR function we can write. If AI and BI, general, you can write AI BI plus AI bar BI bar, or you can write AI BI plus AI complement BI complement. It's the same thing written here. It's a complement values complement. So if you write in the expanded form, you can write A3 XNOR B3 you need to check, and A2 XNOR B2 and A1 XNOR B1 and A0 XNOR B0. Okay, these are the different cases. And this already we explained. That's a final equation we need to write. So already we discussed the case of greater, and here you can see that all the combinations are written. Now we'll discuss how we can write the combination. So this already discussed for greater G. If A3 equal to 1 and B3 equal to 0. So we can write when A3 is equal to 1 means you can write A3. B3 equal to 0 means you can write B3 bar. And then you can say A is greater than B. Okay. So if this particular sequence is 1, the output G equal to 1. Or, so here it is given. Or we can check the other combination. That's why here it is a or is written. Okay, there is an or symbol. Next case, we need to check A3 and B3 are equal. A3 and B3 we can check equal by using an XNOR gate. Okay, A3, B3 are equal and, okay, here it is given and function. So here you can see that and function. Okay, and we need to check one more condition, A2 equal to 1 and B2 equal to 0. A2 equal to 1, so you'll write A2 here, B2 equal to 0 means B2 bar. Then you can say A greater than B. So we can conclude this is another K possibility. So let it be 1 and this is 2 and this is 4, 3 and this is 4. So this is the first possibility. This is the second possibility. Now we need to check the third possibility. Okay, again there is an OR symbol. So you can see that OR symbol here. A3 equal to B3. So XNOR operation. Then A2 equal to B2. Again XNOR operation. A1 is equal to 1. B1 equal to 0. Okay, this is the third possibility. Now the fourth possibility, A3 equal to B3. So A3 XNOR B3, then A2 B2, again XNOR operation, A1 B1 equality we need to check. So XNOR operation, finally A0 1 and B0 0. Okay, B0 bar. So this is the fourth possibility. So this is the equation for G. And the similar way you can write the lower value also. In the previous case, it's greater symbol A3 equal to 1 and B3 equal to 0. If it is less means A3 is equal to 0, B3 is equal to 1. Okay. So instead of that, this is a G function. While looking into G function, you can write L. So in place of A3, okay, you can write A3 bar. In place of B3 bar, you can write B3. And next one is XNOR. Here it's also XNOR. Then A2 B2 bar. Here it becomes A2 bar B2. The other two values are XNOR operation, same thing. A1 B1 bar, here it becomes A1 bar B1, just opposite. And finally 3 XNOR operation, and finally A0 B0 bar and the G function. In L function it's A0 bar and B0. Okay. Now we can draw the circuit diagram directly by writing the equation by looking in the previous diagram, G, L and E functions. So this is G function and this is E function and this is L function. Okay. So directly XNOR gate is connected here, but from the XNOR gate we can use. In some textbook they will return another case which is already we explained in a 2-bit case. So for example, here it is also the same thing you will get here. So this is actually A3 bar. So this is A3 bar and B3. So here in the lower portion, you'll get A3 and B3 bar. Now we are performing A3 bar B3 plus A3 B3 bar, and this is a NOR operation, so the whole bar. Okay, which is simply the XNOR operation. So A3 XOR B3 the whole bar, which is equivalent to XNOR operation. Okay. In the same way, you can perform the remaining set. All these groups are same. Okay. So you can implement L, G, and E. And instead of this, you can use one IC which perform this 4-bit comparator circuit, because you can see that it's a very big circuit. But instead of that, if you get a single IC to perform the same function, that is known as 7485. So 7485 is a 4-bit magnitude comparator. Comparator IC, you can see that all the values. Here you can see that A equal to B, that is equal line. This is A greater than B, G is A less than B. Okay. The inverse also we will get here. Okay. Here you can see that A0, B0, two inputs, A1, B1, A2, B2 pair, and A3 here and B3 here. 16 is VCC and 8 is ground. Okay. Directly applying the input, you will get E, L, G values, and just inverse of that you will get in 2, 3, 4 pin. Okay. By using this 4-bit comparator, you can expand into 8-bit or higher bits also. Okay. This is all about magnitude comparator.